All right. Hello, everybody. Good morning. I hope you are all doing well and everything goes fine. So today we are going to continue topic with the Kalman filter. First of all, I'm going to quick review of what we talked about the Kalman filter. Then we will see what's the problem of the Kalman filter. Then we extend it to the extended Kalman filter to overcome the issues that Kalman filter has. But later I'm gonna also state the problems of the extended Kalman filter, what is the challenge over there after improvements that we have, and later on in continuation, in future we will see how to improve that one also. But we have a couple of other topics in middle to also discuss it. We will see what are those. So in this chapter, we have the Kalman filter algorithm, an extended Kalman filter algorithm. Last week, we talked about some introductions about the normal distribution, how they are physically working, and what are the concepts. So I still see some of you have problems with it. Because of that, today I may give you some practices here, and I will introduce some resources and textbooks that you need to have a look at it, because these are the fundamental and the most important things that you must completely understand in order to understand the topics of the course. Otherwise, that's very hard. So we talked about the covariance and how we can discuss the relationship between two random variables, and how we can talk about with increase in one, how it can affect it with changing the other variable. Then we talked about the normal distribution, individual measurement, the average of measurement. Then we talked about the variance, the standard deviation, and covariance, how we can calculate based on the samples or number of the points that we have in different problems. And we stated that we can compare them to distribution together. So we said Kalman filter is an implementation of the base filter. We already seen how base filter is working, and we wanted to plug it. And we said it's come from 1960s, and the main idea is having the update of the base filter based on the data that we have in real-time fashion. So basically, as I mentioned in this class, we are talking about localization and SLAM mostly. Kalman filter is not limited, of course, for this application, but basically all the examples that we are talking is about the location of the robot, and robot is moving in the environment, either localizing each one of the landmarks or features that we are seeing in the environment, or robot itself can be looked at as the Kalman filter, or the algorithms, that series of Kalman filter family algorithms that we are gonna study. We said this can be including position, velocity, temperature, or whatever we want to measure. We said that it is good linear estimation model, and produces accurate estimation of the unknown variables, new data that are coming in online way to update our belief of what data should be. Kalman filter works with Gaussian distribution. It's very important because we're gonna later see how we can change it, the assumption that we have, and all the calculations that are based on the Gaussian finally results output as Gaussian model for us still. So this is also a key element, and why this is beneficial. So far you should be easily able to discuss it. Why everything in Gaussian is better for us to discuss is that so the probability of the event that is occurring can be distributed by just two variables, the mean and covariance. The mean, mu, and the covariance. or variance. So everything in probability can be represented by only two variables, mean and covariance. And what does it mean? If you remember, these are very crucial to understand the concept. So like if we are talking about robot localization, if this is the x in one-dimensional, and where the robot is, we can talk about the mean. So most probably where the robot is. Or whatever the data is, if this is the measurement of the sensor, the weight, the temperature, or whatever the sensor is, what's most probably our sensor, our machine is reading. Or if we have IMU, what is the value that it is reading for balancing? So all those can be shown as mean, and covariance shows how much error we have, how certain we are that our data is accurate. If we are very certain, our Gaussian distribution will be something like this, maybe. If we are not very certain, it will be less like this, distributed more widely. So that's the very critical point that reduces our computational complexity, and with just only two values, we can demonstrate our calculations and our predictions in the form that we discussed. And as we said, this is the most popular algorithm, especially it has been used in Apollo program. I'm not going to re-explain it again. And if you want to visually see what's happening, we have a bunch of data. What does it mean? During time, you have data that's reading from system. In this particular example, we see the temperature. So you have one temperature sensor. So at time t, you're reading, you see this one. A little bit time goes, you're reading, you see another temperature. And these are the data that you're reading, and lots of errors, of course. So in order to, but what's the ground truth? Ground truth is this line. And in order to, based on these data, in order to estimate what is the accurate value, we are going to, we saw actually how we can use Kalman filter in general perspective. And we are going to see algorithms how to find this line. That this line tries to predict based on the data. New data comes, says, okay, what is the prediction of the, what's supposed to be the correct value that we have. So by understanding this, you see that, okay, Kalman filter is very important and applicable algorithm for robotics. So, or reading any kind of sensor. In most of the applications, we have such data, and we need to filter it. Even if you have very good image processing algorithm, you're finding distance of the landmark, then of course, still there you have some noises. Your calculations and robot shape or the parameters that have will look like data like this in XY. Then you can apply the same algorithm in order to improve the estimation of where the object is. So the simplest way is like you may say, okay, I can get average of data and plot it. But if you get average of data and plot it and compare it, you see that that's very bad estimation. The simplest and the kind of the most basic filter can be the average, but that's not accurate, of course, and Kalman filter does better job. Then we discussed one estimation that we said estimation can come from the filter. So we have again the data here. We have the truth, actual value, this line over there. And based on that data, we can have the prediction. And the prediction comes from the filter that we have. Estimation comes from the filter that we have, and prediction comes from the previous data that we have. So for example, in this particular example that comes from the book that today I also show how you can see implementation code. So if you have a scale, so you're measuring your weight every day, and you know that you're gaining weight every day, and you can know that, okay, I'm supposed to be at like higher weight tomorrow, and a day after tomorrow higher weight. You can guess it. And this guessing in this example is scale weighting. But in our example, we talk about the what? Can you guess it? We talk about the control commands. So matching these is a little bit confusing. Yeah, of course, if you can do that, you understand what's exactly happening. So in robotics application, we say, okay, based on here in this kind of, if you are reading IMU kind of sensor data, we say, okay, prediction can come from our expectation of what is going to happen in future. But that expectation of what is going to happen in future in our basic applications, in robot localization, for example, we are talking as control commands. So based on this knowledge, and after learning Kalman filter, extended Kalman filter, then you can use it in different applications, not only robotics. You just need to plug what you need as prediction over here and try to estimate it. This prediction is not limited only to control commands. This can come from any resources of any sensor reading or the prediction that we have based on the data that we have. So another example, I'm not going to re-explain it again. Some applications we've seen. We've talked about the navigation, control, time series analysis, robot trajectory optimization, noise filtration, and the estimation of the current of the, for example, a motor system that is getting feedback from environment and we want to compensate. Compensation is like, for example, you need your motor needs to lift this, okay? How much torque you need to add to the motor to lift it. And based on the reading, Kalman filter can give you better estimation of how much torque you need. Because if you give more, it goes higher, right? You need exactly the correct amount to hold it like this. My brain does it for me for now. My finger, I have enough force to hold it like this in this angle. But if you want to do that without position control, with torque control, if the motor that you have, then, for example, you have simple DC motor. You don't have position like servo motor that you can say exactly go stop here. Then you need to actually that servo motor inside already implemented this for you. That how much force needed to be applied to exactly to stay over here, based on the external weight that we have. So that can go and Kalman filter or extended Kalman filter that later on we will see can do this job for us. Any question? So we said that we consider as observation and motion models, and we consider they are linear for Kalman filter. Then we indicated and declared the motion model as xt, that we said new state is equal to xt minus 1 times the matrix n added by the mode control command, the matrix m added by the motion model noise that we have in the environment. And we discussed that these n and m are kind of mapping of the how motion model can be applied based on the previous poles and control commands that we have, kind of linear matrices. Then for the same thing for the observation whatever can be, LiDAR scanner or image processing, whatever it is, you have some observation that observation still has some error, and a mapping, a matrix that can be kind of scale our observation model. So here we discussed what are the important elements. I'm not going to re-explain it again. We just want to have a quick recap. Then some elements, what we have here. Okay. Then the explanation that we discussed in details last week. Later on, I started to talk about the basic probability concepts in the robotics, and we talked about how, for example, tossing a coin can work, and how we can bring it to to Gaussian function form, so that Gaussian function form in the probability can be moved to the multi-Gaussian distribution, so that if we have one variable, one D is like this. But if you have two dimensions, it looks like this. And because, of course, Kalman filter can work in multi-dimensional scenario, we need to consider the multi-dimensional or multivariate Gaussian distribution. We discussed how this can come to the form of the multivariate Gaussian distribution. I explained this last week. I'm not going to redo it again. So that because this equation here, the aim of the Kalman filter was using this term over here and combining it with these two. I want to show together motion model and observation model. We want to plug these over that term in order to have the update rule of the Kalman filter. That we just kind of plug them together. That we had the kind of a big term in order to do that. So we saw that, okay, the same multivariate Gaussian distribution, we plug the part that we have for motion model into it. That to doing this, we said we have motion model with Gaussian noise. So it means that we actually bringing our motion model that robot is moving based on the control commands in the environment, and we want to also consider the noise that we have over there. So we've written this rule. Then the same thing with the same combination and the term. What we've done last week, we discussed that we can write the probability of observation given by xt with this term over here. That's what we did, multivariate Gaussian distribution combined with the observation model that we discussed with the matrices that the W that we have. And I stated that this Q is for the observation error, and here we have R for control error. So it is still this, the Gaussian noise that we have in our control commands and observation that we have. And usually that's with zero mean, and the covariance indicates the amount of error. What does it mean? It means that, like, so if I say my robot is over here with some certainty, with some belief, so I can add noise here. So if I want to add noise here, I have another noise that this mean indicates some x's, like from 0, for example, to 100, some values here. But I want to add some error over here, so I don't need the mean, basically. So when I don't need the mean, so I have, like, you may say, this is my error. So mean is not important because I don't care where it is. But the covariance is important for me. I plug it to it, and this will be like move the shape, just make it wider if you plug it to this guy over there. How you can plug it over there? So of course you need to know how to add two probability distribution function or multiply them. I know you have still some problems because of that. I'm going to give you some practices based on the questions that you've had since last week. Now, for example, if I want to explain the add, of course, it's easy. You can add the mean of two probability distribution functions. If you can sum them, we have two values. And for the covariance, you can sum them, right? Then you can shape new this probability distribution function. So that's very simple. Now you can, like, if you have two, another one over here, you can sum the mean, and you can sum the covariance. Then you can measure them. But basically, we don't do that. We just use the sum for adding the error. But of course, for multiplication today, you will see how even in Python you can implement it based on the things that I'm going to define for you. Then anyway, let's continue quick review of what we've discussed, because we're going to need them. Then we move toward the, so we saw the basic intuition of the Kalman filter. Then we said that we want to plug that term that we achieved together into the base filter. What was base filter? Base filter had two steps: prediction. In the prediction, we were calculating predicted belief based on the probability of the xt given by previous xt and motion command times the belief that we have. And the belief is related to previous belief that we calculated over here. So after prediction step. At the first starting run, so it is the initial belief that we have. So when I'm talking in the initial belief, if we are talking about localization, I'm believing that I'm somewhere in point 0, 0. How certain I'm believing based on this covariance that I have. If I'm quite certain, I can say, okay, it's very sharp Gaussian distribution. No, if I'm not certain even at the initial belief, then I can plug it there. That you've seen example implementation, for example, the chapter that we were discussing about the base filter, if you remember. So after doing the prediction, predicted belief we have. Predicted belief means that, very important again. So my robot is over here. I'm running go to 3 meters, for example. Then I know this control command. Then I want to calculate the predicted belief where I am. Based on the control commands, previous pose that where I was, and previous belief that where I was. Okay? And don't mix these. This is the belief of the calculation Kalman filter, and this is the pose. If we are talking about the X, Y, and orientation or bearing. Then second step was the correction. So in the correction, we were trying to correct this estimation that we've had. What does it mean? So I was here, I moved and calculated my belief where I am. That is like, again, Gaussian distribution. Then I say I need to correct it because I have lots of error on the control commands, motion commands that I moved over here. And how I can correct it? I just can look around with observation, get information. I have another model. Then I can improve this. That if you can see, predicted belief can be improved by the observation, the probability of the observation. Then just normalize it so that you can plug them two together. This was base filter that we studied. But now we studied also Kalman filter. And what's the objective? We saw two super big equations that we want to plug it over here. Instead of having the probability of the xt minus 1 ut that comes from motion command, we want to plug that big term over here. And here for observation, we want to plug that big term over here to use the base filter in order to update my predicted belief and belief of where the robot is in online fashion. So everything clear so far? I'm just reviewing what we've studied so far. Okay. Now, what we've done, we said, okay, instead of like plugging there to have very big equation, directly we went to see the algorithm, and we saw that we can have a Kalman filter algorithm that gets the mu t minus 1, mean and covariance. Mean and covariance at the beginning will be initial belief where I was at the beginning. I told you where the robot is can be indicated by two values, mean and covariance that says where I am in the environment. So to make sure that you get the idea 100%, so let's say this plot shows my whole environment X. That is continuous, of course. Can be continuous because we are talking about the Gaussian distribution, and you can say my robot can from here 0 0 up to n part can go to there. This is whole my environment. And what can I do? I can say where the robot is. What's my initial belief? I'm believing robot is here. I'm drawing a small here. And we say, okay, with mean and covariance, I indicate the initial belief is there. That comes to the algorithm in the Kalman filter. And of course, the control command and observation also is an input for the Kalman filter that can be in online way, that each time I'm sending to the Kalman filter, or if I have all, send it to the, depending on implementation that we have, send it to it. But still in the loop that we have, we will update it each time, just predicting and updating 2 steps. So what we've done, we first calculated the prediction. The prediction came for the predicted mean and predicted covariance. So this predicted mean and predicted covariance come from where was the initial robot and what was the control command that I've had and what is the observation. Observation will be used here. For now, control command we've used. And we've used the matrices, linear matrices, to update the mean and covariance. That I'm not going to, again, explain very in detail. Last week we did it. In correction step, first we calculate the Kalman gain. And we said that Kalman gain is indicating how important is the control command and how important is the observation model that I have. So again, my robot from here moves here, sees, in order to update, I'm saying now observation is more important or that one that I came is more important. That Kalman gain was helping me to calculate it, that this Kalman gain, if you look at here, indicates that observation or control command. So here we have predicted mean. Predicted mean is where the robot is, mean. So this is new mean, is equal to in the left part we have the predicted mean that calculated directly from motion command, right? And in the right side of the term, we have Kalman gain that is multiplied by the observation. That if I last time also showed some examples and discussed it together in next slide that we have, that if we can change the amount of accuracy on the observation and on the control command, how it can affect the change of the updating based on the observation or predicted motion command, predicted mean that we have. It's kind of adjusting the value. But what was the benefit? The benefit is that you don't need to do anything. You don't need to say, okay, my robot is like, you can of course put some weights over here, but Kalman gain already calculates it automatically for you based on the amount of error of the control command and amount of the error of the observation model that you have. Automatically adjusts it. If you have very accurate observation model, then it ignores especially the control command. Says seeing is better than anything else. Have more weight on it to predict where the robot is. The mean, like this one that is moving. Then that's it. This was the whole structure of the Kalman filter. Last week we discussed. I'm not going to go in detail again. We saw some notes, for example, how correction, how the matrix operation can be done. Yeah, here I showed that if we don't have error in observation, it means that Qt is equal to 0. What was the Qt? The observation noise that we have. So if it's 0, what is happening? We discussed that then observation will dominate the output, and it is already proven by the Kalman filter. And I also replaced, if you replace yourself again, you will see that how in matrix operation this Kalman gain will give all the weights to the observation, because this becomes 0 over there. Then we saw the example and how it's working. So we have in this class more than 14 chapters. Mostly in all chapters we have this robot over here, but last week I saw that you have some problems in visual understanding. For future I added this. Now you can use this one too. So that we had the initial belief. What does it mean? It means that our robot is over here. This can be any kind of robot. I put humanoid robot mostly. So humanoid robot is here, and my belief based on the mean and covariance indicates that I'm there. Then what is happening with Kalman filter? So robot measures the environment, uses any kind of sensor that it has, measures the features from environment, and that measurement says, okay, robot is like over here, not there. Measurement says this. So what does Kalman filter do? Wants to, based on the calculation of Kalman gain, and based on the certainty of each one of these, that is now very clear, to update the belief of where the robot is. How that is happening? So it is happening like this over here. That the belief is changing based on this new black curve, Gaussian distribution. Then we are updating where we are believing that the robot is. Then we said that, okay, we're running control commands, motion commands. Robot moves from there to here. So after robot moves from there to here, of course, our belief is moving based on the first step of the Kalman filter that we have, moving to the right. But we have the noise. Based on the noise that we have, that's the reason why this curve that is sharp here becomes uncertain, more uncertain here. So this one becomes more uncertain because of the control command or odometry or the motion model noise that we have. So we move more, this becomes more uncertain because noise becomes bigger. Accumulating of the, we said, okay, if your robot is going a little bit to the right, there will be where, like, if you want to go there, you end up there. This creates curve and more uncertainty during the movement. And because of that, in Kalman filter, observation tries to correct our belief based on that. Okay, we say after some movement, robot again sees, and after the seeing, we have another curve, this one over there, and Kalman filter again updates the new belief for us. So this was recap of all what we've discussed last week. Of course, if you want to implement, we have implementation notes that we will see next chapter. First, we have a couple of new topics there in order to be able to go in details of how implement it. But directly we will go to extended Kalman filter, and in next chapter I directly go to implementation of that one. I will open it later, the whole equations, to how we can really bring it to the practice in localization problem. So what was the shortcoming over here? If you remember, we said that we have all the time linear measurements, and error will be considered as Gaussian distribution and linear. Let me write bigger. But is it realistic? Is it always happening in real environment and all the errors that we have always is linear? Of course it is not. In some applications we do, but in many applications we don't have linear error in our system. So nonlinear model can cause non-Gaussian model of the noise or prediction or whatever we have. Now, the challenge is, if you have a look, we were talking about mean and covariance. Then we don't have it anymore. Can you show this with mean and covariance? No. So this is, if we want to consider non-Gaussian model, of course we will be happy because we have more accurate prediction of the data that we have, the error that we have, then our final prediction will be more accurate. But we cannot do the same thing with mean and covariance. What to do? Due to this problem issue, we have extended Kalman filter, and we will see how to deal with this problem. So is everything clear? The challenge that we have? The main concepts are clear for everybody? Oh, what happened to this guy? Okay. So the idea behind is simply trying to use mass, the power of mass, to somehow convert this non-Gaussian model to Gaussian model again. The whole idea is this. Try to use mass to convert this to the Gaussian model. Of course, we will lose some, but still we will be able to deal with nonlinear model of the environment. Because if your sensor noise is nonlinear, non-Gaussian, or better to say non-Gaussian, then you cannot use Kalman filter anymore. If you feed it to Kalman filter, the result, the prediction will be totally wrong. In order to be able to use it, we have extended Kalman filter, and we will see how we can linearize nonlinear function like that. In order to be able to do that, we should have a look at some mass background, then quickly see how we can convert it. But the most important one is the how we can finally convert the term. So extended Kalman filter is again one implementation of the base filter. It is a nonlinear version of the Kalman filter. Everything else is same almost. We just want to bring nonlinearity. So again, we have estimate of the current, mean, and covariance after conversion. And assumption is that next state probability and measurement probabilities are governed by nonlinear function g and h. And we are going to see how we can calculate g and h. So if you have a look here, the idea is the xt and the ot as like observation and the pose, we want to rewrite them in a form that we don't have linear matrices that we used in Kalman filter. So if you remember, we used the matrices n and m and w in order to have presentation of the linear estimation of the environment. Now we want to replace it with a function g, that this function g does the same thing, does the exactly same thing, but can get the nonlinear model, can get the non-Gaussian distribution. So that we will talk about how these g's can be implemented, can be declared, and how this h can be declared. So g is indicating getting the control command ut and xt minus 1. So gets the pose and gets the control command, exactly the same input, but this time non-Gaussian, so that g can model it. And we add some error to the motion model that we have again, epsilon t, for example. The same scenario is for the observation model too. We want to indicate and declare function h that will be replaced with the w, matrix w, that it gets the xt, and we add some noise, and we have our observation. So we say EKF calculates an approximation and replaces this approximation by Gaussian. So that this G and H is doing that. So we are kind of in extended Kalman filter approximating based on these functions. We don't have exactly the precise value. If you are familiar with like neural network already, we have very similar concept over there. We have model that our model is trying to predict the output. But here we are not going to use that complex models. We are going to use simple math to achieve it. So what is happening? Let's have a general look at the differences. We have Kalman filter. And in Kalman filter, we were calculating the xt by matrix n and matrix m based on the control command, based on the previous pose for motion model. And for observation model, we were doing based on the xt wt matrix w to get the observation based on the error that we have. We already seen this so far for Kalman filter. Now what we are doing, we are just replacing the function g with ut xt minus 1. So this is the ut and this is the xt minus 1. And here xt for observation with the function g and h. So in order to achieve this, we are going to use first order Taylor expansion to linearization of the nonlinear model. So what is the first Taylor expansion? It is constructing a linear approximation to a function g from g's values and slope. It uses the g's values and slope. What does it mean? It means that if we have a non-Gaussian model, then the idea is use the, for example, if you have a point here, use the slope and the value where it is in order to linearize nonlinear Gaussian model that we have. So in order to calculate the slope, we are going to use the partial derivative. As you know, I already mentioned in the class how you can do that. Also, I think I will include it in the slides so that you can see here, especially visually, I added recently, that you can see how with calculation of the partial derivatives based on the given slope, we can use this to calculate the g prime of the ut and xt minus 1 based on the control command and observation that we have. So keep this in your mind, that we have the concept of derivatives and the slope and value in order to achieve it. Now, based on using that, we are going to define the first order Taylor expansion. So first order Taylor expansion is a polynomial linear approximation of the function that it says we can have the intercept of the line with the model that we have in order to calculate like kind of, if you have this model, we can model it to this line over there, linearize the nonlinear model that we have at each point. And of course, each one of these points during time that we are going are nonlinear, right? So we can kind of, the idea is, okay, for each one of these points, if I can draw this for each one of these, then I can kind of linearize nonlinear model that we have. So this is in one dimension, like it's simple. That if we want to do that, we can calculate the Jacobian matrix. And how Jacobian matrix is working. Jacobian matrix is like n times n matrix that has all its partial derivatives. So all of the possible partial derivatives for the model that we have can be included in form of the matrix that indicates what we've seen in previous slide. It generates the high dimensional space. It kind of linear approximation of the, so let me bring the model. So linear approximation of the non-Gaussian model that we have. For example, if you consider in 2D, for each one of these single points, we can calculate the line and the slope of that line. And if you want to calculate for whole model, and for each one of those independent points, what we can do, we can approximate linearly with this plane that we have. Kind of, we have the model that we are flattening to some prediction over there. And in order to do that, we are using Jacobian matrix. That this Jacobian matrix does this for each one of the points that we have over there in form of first Taylor expansion. So we also this is like known as generalization of the high dimensional space into the linear approximation of the function that we've seen. So the general idea, so now you can see that, okay, if we have non-Gaussian model like this, the general idea comes from this based on using Jacobian matrix. So by knowing that, now let's use it to plug it into the Kalman filter based on that knowledge that we have from mass. What we had the observation model in Kalman filter, means that robot. We have the motion model, sorry. We have the motion model that robot can move in the environment, and we had the prediction. Now, we said that in EKF, extended Kalman filter, we want to write it in form of G, so that the inputs can be non-Gaussian. The control command and xt-1. So, but this is non-linear now. In order to linearize it in Kalman filter, extended Kalman filter, what we do, we use the same concept in order to achieve it. So we replace this term over here by writing it in linearized form. How that is happening? So it is happening by changing this xt-1 to the g of the ut-1, that is the previous estimation that we have, added by this term over here that actually does the linearization that this G prime is Jacobian matrix. That Jacobian matrix that is flattening is applying on the model that we have. How that's happening, also we have the term here, what we have, xt-1, the differences of the pose and the mu-t, the previous belief and the previous pose that we have. Differences of that linearized, so that I think I've written here, the term, this term can be written in form of the Jacobian matrix and the same input that we have. And this is the gt, that is partial derivatives of the all possible states that that function can be linearized. So the idea is simple, but but maybe looks a little bit complex. What we need to do, in fact, the xt for motion model as g can be written as this part over here, simply. So only you need to consider that, okay, instead of the matrices in Kalman filter, in extended Kalman filter, we are going to replace it with g of the control command xt minus 1, that this term is equal to this term over here. That whole the discussion background is using the Jacobian matrix in order to linearize it. So now we did it for motion model. What about observation model? For the observation model that we had correction, robot sees something, we are doing the same thing, same linearization, but this time instead of the matrix W in Kalman filter, we are replacing with hxt, and this is non-linear. We linearize it by the same scenario over here, that we are adding the ht here, h of the predicted mean added by the Jacobian matrix of the xt minus predicted mean. That is differences of like my predicted mean and the differences with the xt, and how this can be plotted to the Gaussian model, to the linear model that I have, if they are nonlinear as input. So the same Jacobian matrix over here, that can be correct our observation model. So with using this idea for observation and replacing with this term, we can achieve linearization of nonlinear model. But so far, we've seen just general concept and general idea of what's happening. In next chapter also, I'm going to go a little bit more in details of how this is happening over there. Now let's have a look what we've had in Kalman filter. Look at the term that we have here. We had the predicted belief of xt and whole this big term to calculate, right? With matrices n and m. So in EKF, what we do, we replace the matrix n and m with the g. That is linearized form of these matrices. So if you remember, these matrices were kind of helping us to mapping the pose and control command, right? But here, now we are using the same, we want to do the same thing with G and the Jacobian matrix, but this time I can feed non-Gaussian model inside. And this is happening with first order Taylor expansion. And if you think that you need to understand it more deeper over there, you need to also have a look more in depth of what's happening over there, write some calculations, and the examples that we will have, you will see how really it is happening. Of course, we will have also implementations later. You will do some practices also in order to understand it better. So this is EKF for only motion model. And what about the observation model? With Kalman filter, we had this term, right? That later we wrote the algorithm also. And now with EKF, we have this term over there. What we do, instead of the matrix W, we are replacing with the H. This H and this Jacobian matrix that calculates and linearizes our input for us in observation. Now let's have a look at the algorithm directly. How does it look like? So hope you don't have any problem in Kalman filter, because we are going to compare it now and see what is the idea over there. So in Kalman filter algorithm, we had the mean, covariance, control command, and observation, and we use the matrices N, M to first predict, then update using Kalman gain. But let's have a look here what we have in extended Kalman filter. We have the same prediction step over here, and we have the same correction step over here, and we have the Kalman gain again there, right? Only thing that we are changing, replacing this matrix N and M with the what we've achieved with mass, replacing with G of the control command and mu t minus 1 here for the mean, predicted mean. And for covariance, we're using the Jacobian matrix of the calculations that we have Jacobian matrix of the previous covariance added by some error. So simply we replace this N with G here. That is accepting non-Gaussian model. So after calculating the predicted mean and predicted covariance, what we're supposed to do, calculate the Kalman gain in order to see, is this part important or is this part important to update my prediction. And again here, Kalman gain can be rewritten by there. If you have a look at the Kalman filter, we have matrix W's that I discussed, explain in detail why those are there and how we can, like with replacing, how that's working. We just change it with matrix H. That matrix H is again non-Gaussian. This is the matrix of partial derivatives that accepts non-Gaussian of the observation model for my filter that I have. Then after calculating the Kalman gain, now we need to update this predicted mean and predicted covariance by observation. That again the same thing with replacing H mean t and the matrix of the HT that can accept non-Gaussian model for me. So with having a general look, we see that we've used the mass, we've used first order Taylor expansion, the idea, the concept of using partial derivative matrix. Now I can give nonlinear model as input, and my algorithm now is just replacing, is just converting the non-Gaussian model to Gaussian model and solves the problem. But who can say now what's the problem here? So we achieved something with extended Kalman filter, but what we are losing now? So first one point, so can we implement it now? First question. Can you write the code? Do you think? No, not yet. We have a lot to do still. We have some to do. Next chapter, we are going to study its component, and later I'm gonna open it. Like you will see, we have super big algorithm and lots of equations inside. That's why you have like, oh, I don't understand what's happening, like what. So we are seeing for now general concept of the extended Kalman filter. We're going to open it. And also, for example, we've seen the control command, and we've seen the motion model, right? By velocity-based motion model, for example. We've seen the implementation. So that's one component that we're going to plug it in. But we haven't discussed about observation model rate, right? What can be observation model plugged to here? So next chapter I'm gonna explain how observation model can come here. Then we put all together and we will have a big algorithm over there. So still no rush. You cannot think about implementation so far. Because last week some of you were mentioning we can implement or have practice. So not yet. Okay, now let's go back to the question. What we are losing here? No idea? We are losing something very important. I mean, it's kind of drawback of the extended Kalman filter. That later also we are gonna improve it with another algorithm. Time. I think I've shown the complexity. Okay, so here, before going to also clarifying exactly what is the cost over there, but we are losing the time, and our algorithm is more complex. Here I've added some notes for you guys for later to read and understand the algorithm better. For example, G is here, a nonlinear model. I already explained all of these. So, for example, the mean t minus 1 is output of the extended Kalman filter from previous step. That shows this one. Where it is? So this one predicted the previous mean, and for example, we have predicted belief. That predicted belief is equal to predicted mean, and it means that where the prediction and my belief that I am. We have the covariance matrix of the prediction belief and previous covariance matrix, and GT and RT is the motion, the Jacobian of the G, and the motion command noises that later when you are studying you can understand exactly what's happening without going too back to the slides to understand what was it. So I added some notes for here. I explained all of these today for you. Yeah, here. Here we say, okay, in the extended Kalman filter, we linearize all nonlinear functions and added linear approximation of the nonlinear functions so that the time complexity is the OD2.8 added by n squared. So what does it mean? It means that, so for D2.8, we need to have matrix operation, that this matrix operation in size d times d cost us this, d to the power of 2.8. If you want to have a proof, just check it yourself. And this is added by the n dimension of the state space. So state space is with n dimension, and that can also cubic cost that we have. The cost is still acceptable, but this is, you see, 2.8 is quite high, and that kind of limits us in using extended Kalman filter everywhere. We will see. Because if the state space and number of, for example, objects that we have is too much, like features, you have dozens of features that you want to localize in the problem. After next chapter, you will see that this is big problematic situation that we go toward the uncentered Kalman filter, and we will see how uncentered Kalman filter can fix it. So here the things that I explained to you. So we have point and slope and linearize it, and during time, and we need to do it for all of these, and that's why the calculation is very costly. So in this chapter, what we've seen, if we want to summarize, we discussed the Kalman filter first. We then saw the motion model with Gaussian noise. General concepts we reviewed. We've discussed observation model with Gaussian noise, how it looks like. We will see later in details. We discussed Kalman filter shortcoming after we discussed it. That we saw the problem is that it cannot accept non-linear, non-Gaussian models. And what we've done, we introduced extended Kalman filter that can solve it with linearization of the Gaussian distribution, non-Gaussian distribution. Then finally, we linearize it and we solve the problem. This is the end of this chapter, so that if you have any question, you can ask. Okay.